Hello, good day. Wasiu Adekunle is my name. This is the first series of my presentation as far as the discipline of econometrics is concerned. So this morning I'll be presenting an issue that is one of the violations of the classical linear regression model assumption, and that is the problem of autocorrelated errors. When you see autocorrelated errors, before we even go there, the particular assumption that is being violated here is the fact that errors are not expected to be correlated across time and space. But in a situation whereby errors are correlated across time, we call that autocorrelation. That's the autocorrelation problem. In a situation whereby errors are correlated across space, we call that serial correlation, spatial correlation, positional dependence. So today I'll be taking us through the problem of autocorrelated errors. So this particular presentation was prepared by Wasiu Adekunle and Olawale Ayola, which was an assignment submitted to Professor Olawale Obukola of Economics University of Ibadan. So, matters arising, the outline of today's discourse will be rendered in 5 sections. Now, the first section is the concept of autocorrelation. What do we mean by correlation? So, what are the causes of autocorrelation with real-life examples? What are the consequences of autocorrelation problem existing? What are the various for the existence of a correlation, and how do we go about resolving the problem of a correlation? So, like I rightly said earlier, autocorrelation is a situation where the error term associated with an observation is correlated with the error term associated with another observation. So it's a direct violation of the classical assumption that errors should not be correlated and must be independent of expanded variables. That's the no autocorrelation assumption. But this problem directly affects many time series data, hence the name autocorrelation. It's also a commonplace, okay? It's also a commonplace in functional data. Hence the name serial correlation, or spatial correlation, or spatial autocorrelation, or serial or positional dependence. You have autocorrelation and errors across time. And when you have a model where the error term depends on its first line, it is subscript t minus 1. And then the assumption there's been variance between error term in the current period and in the adjacent period should be equal to 0. So, but when this assumption is violated, such that the covariance between 2 adjacent error terms across period is not equal to 0 for all t, then there is a problem of autocorrelation. And then in econometrics, when you have a model, ET subscript T equals to rho E subscript T minus 1 plus epsilon T. ET is a current value, T minus 1 is the previous value, while rho is the coefficient of autocorrelation. So since this model follow a AR1 process of correlation, autoregressive process of order 1, so we call that rho the first order coefficient of correlation. And epsilon you have there is said to be orthogonal. When you say the error time is an error time is orthogonal, it implies that it follows normal distribution. It is independent and identical normal distributed with zero mean and constant variance. So in that wise, we say that that error is a white noise. It's orthogonal. Just the case with autocorrelation across time, we can also have across space. And that's speaking to model 1, model 2, where error time associated with procession I is a function, a linear function of the error associated with observation J, procession J. So when this problem subsists, then the covariance between the error terms across space, across units I and J is not equal to 0, so I is not equal to J. This assumption that I is not equal to J is very important and key, because if we have the assumption that I is equal to J, we're going to have covariance EI against EI, or covariance EJ against EJ, which is just equal to the variance of the error time. And one thing we should know there is that just like in economics, there's an assumption called ceteris paribus. In an attempt to examine the impacts or determine the impact of one variable in nth number of variables, or in kth number of variables, you need to keep k minus 1 variables constant so that you can know the impacts and examine the impact of the kth variable on your dependent variable. So in this case, when you say and assume that autocorrelation exists, we do not assume heteroscedasticity exists. We assume there are no other foundations that exist aside from that autocorrelation problem. So if I rewrite this model and not assume it and put the assumption that I is not equal to J, then I will conclude that the error term EI is homoscedastic, and that is what it is, because we are looking at a problem that is not associated with violating that assumption of homoscedastic. So we are looking at the problem of autocorrelation. So the autocorrelation problem when we look at it, we make other problems, or we ensure, or we assume other problems to exist. Okay, so the rho we are saying in model 2 is the coefficient of linear correlation between the two errors associated with processions I and J. Next, causes of autocorrelation. We really have an example. The first, we have inertia, we have lag, we have non-stationarity. Grouping these three things together, they have similarities, but do not mean the same thing. Though there is one thing that associates all of them together. That is the case of persistence effects. When you say inertia, variables exhibit, economic variables naturally exhibit sluggishness. And that's the reason why in macroeconomics we have what's called sticky price macroeconomics, and we have flexible price macroeconomics. And variables that exhibit inertia, there are variables that have low frequency, data frequency. More especially like GDP that you can get monthly or daily figures for. So they exhibit some form of inertia, unemployment rate, inertia, poverty, inertia, and so on. So all these variables, they are called low frequency variables or series, and they exhibit some form of inertia. So when anything happens to the economy, it takes some time for them to adjust to that shock, whether it is internally, externally transmitted. Okay, so because of the fact that they exhibit sluggishness, that implies that there is a form of lag in response of such variables to shocks. And because of the fact that there's sluggishness in the behavior of the series to shocks or responses to shocks, and there's lag, then we can say that that series may suffer, I'm using the word may, from non-stationarity. Because in a situation whereby a series exhibits a characteristic of not being predictable, when it is supposed to respond to shocks and it's not responding, no one can tell when it will respond. And let me tell you here, in the works of Nelson and Fossa, these guys are the ones that originated the issue around stationarity. You can read their paper. I read it, and I refer you to my thesis that's published on ResearchGate. You can request, and I send to you. So it is detailed in that paper. Okay, so in a situation whereby a series exhibits sluggishness and lacks in relation to shocks or response to shocks, then there are persistent effects such that the impact of the shock will not just end immediately, or will not just have a short memory. It has something called a long memory. And because of that, let me give you an instance. We know Nigerian economy is characterized by cyclical behavior in response to oil price shocks. But for me, we more respond as a country to negative oil price shocks than to positive oil price shocks. Because currently Nigeria oil price is selling for over $70 per barrel on the global market as we speak. But as that's translated to improvement in economic activity in Nigeria. But let's just assume that oil price suddenly crashed. Then you can see that impact on the Nigerian economy. You can feel it. Even the layman on the streets can feel that anomaly. So because of that fact, you can recollect oil price started crash in third quarter of 2014. At least oil price, global prices crashed from 3 digits. And that continued till oil price dipped as low as $30 per barrel. In fact, $20 per barrel sometime in Q1 20. But unfortunately, given the vulnerability of Nigerian economy, oil price shot negative. Nigerian economy could not reverse the recession in the second quarter of 2016. And that speaks volume. And this recession lasted for, let's say, 4 quarters. We plunged into recession in the second quarter. We're still in recession in the third quarter. Fourth quarter, we're still in recession. Third quarter, first quarter of 2017, we're still in recession. So it lasted for 3 quarters because Nigeria economy recovered again in Q2 2017, the second quarter of 2017. But since Nigeria's recovery, despite the recovery of oil prices, you can say Nigeria's growth has been very weak and follows a weak trajectory. It oscillated between 1% and 2.6% during COVID-19 in the year 2020. But before COVID-19, just before COVID-19, or during the height of COVID-19, when it was declared a pandemic, there was a subsisting oil price war between 2 oil giant countries. I mean, that's the big brother OPEC and the big brother OPEC Plus. The big brother OPEC, Saudi Arabia, and the big brother OPEC Plus, Russia. Added with the impact of COVID-19, oil price dipped was $9 per barrel sometime in April 2020. Brothers and sisters that are listening to me, the Nigerian economy could not escape a recession in the third quarter of 2020. But this time around, the recession was just a brief one. So according to the MBS, the recession lasted for 2 quarters. That means 2 quarters or even 1 quarter. Nigeria escaped from recession in quarter 4 of 2020. Now the economy started its recovery, came out of recession, recording 0.1% growth in Q1 2021. That rose to 0.5, I think. Now in Q2, due to business effects of COVID, so we grew by 5.055%. So if we now plot the kind of time plots of oil price, global prices against Nigeria's GDP over time, you'll find that there is some form of asymmetric relationship. That's not even where I'm going. Where I'm going is the persistence effects. The fact that oil price dipped for a longer number of months and the economy also follows suit. Because, okay, let me put it as that. So when a series exhibits a long memory due to persistent effects, we can say that the series exhibits the problem of autocorrelation. And that's usually common with, don't forget, that exhibits inertia, sluggishness, that has lag effects, and that does not follow a stationary path. Quite unpredictable. So the second cause, underlying causes, one of the underlying causes, key one, is specification bias or misspecification error. When you say specification bias, it can come in two forms. It's either that you are bringing in a wrong functional form, or you are excluding important variables. In the case of a omission of important explanatory variables, let me just give an instance of the demand function that you are to estimate, where you fail to include the price of the product in question in that model or in that demand function. Then, because of that, that excluded variable will correlate with the error sign because it's an important variable. And when it happens, then there is an autocorrelation problem. Likewise, wrong functional form. You have to estimate an average cost function which is U-shaped, non-linear, but you fitted a linear, but you impose a linear fit. So the model is going to suffer from autocorrelation because the square term, the quadratic term, has been excluded, and it's given the fact that it's very important, it will surely correlate with the error. And the problem of autocorrelation is the end of the day. So the next one is the cobweb model phenomenon. The cobweb model phenomenon. So what do we mean by the cobweb model? This cobweb model is being applied to agri production, especially because the demand for agri products is a function of its current price. But rather, the supply of agri products or produce is a function of its previous price. How do I do? Let's assume in the last season, planting season, the farmer had a bumper harvest. So, last year when the farmer had a bumper harvest, he was able to supply more to the market. And you know the law of supply. What that has been informed, the higher the price, the higher the supply. But in a situation whereby supply comes first, such a way that we have a kind of inverse supply function where the price of the product is a function of the supply. Then when supply increases, given that demand remains constant, the impact of that is for price to naturally fall so that the supplier or seller can sell at a good market price. But in a situation whereby the farmer supplies too much to the market in the last planting season and at a very low price for its products. So the next planting season, which is the current one, is going to supply just little. Because now in the current season, what determines the supply is the previous period's price. So because of the fact that there is a kind of linkage, a kind of persistence between the previous period price and the current period's decision of the farmer, supply decision, then there's a problem of autocorrelation. So when you are dealing with a covered model, you have to account for lags. And it's usually applied most especially to agricultural production. Okay, we are moving. So what are the consequences of the existence of autocorrelation? One, the expected value of the error term across time or space remains zero. The error term, however, is almost stochastic. Like I said earlier, it has constant variance across observations. So you will recall from equation 1 that error term follows an AR1 process, autocorrelation scheme of order 1. And that I recall here. So if you take the expected value of this error term, you're going to get 0. But if you take the variance, you're also going to get something constant, given the assumption that there is the assumption of stochasticity is not violated. So implying that one of the consequences is that given the fact that the expected value is 0 and the error term is the question is almost stochastic. So that's one of the consequences. So implying that the only problem we are assuming is autocorrelation. So and the fallout from that is the fact that OLS estimates are still unbiased and may be consistent in large samples, that they are asymptotic property, despite the presence of autocorrelation. So which implies that, so if you look at equation 4 implies that the expected value of the estimator, beta, or B, is equal to the population parameter, beta. So an equation 4 implies that the expected value of the estimate, the test sampling, is equal to the true population parameter. So since the errors are now correlated with each other across space, across time, in this case, the covariance variance matrix for the errors have non-zero elements along the off-plane diagram. The existence of autocorrelation in errors implies that the error variance is particularly overestimated. How do I mean? When you have a matrix representation, you can have the variance covariance matrix. Okay? Variance covariance matrix. Okay, let me call it a day here. So in our next lecture, which is tomorrow morning, by the special grace of God, or any other time, we would pursue this particular section of the paper further. Thank you. Thank you. Thank you for your attention. God bless you. Bye.